Any questions about intermolecular forces or polarity or anything else?
Are we talking about, was it crystalline structures today?
Yeah.
Okay. I got no point in life in mastering chemistry, and I'm like, what?
All right, yeah.
Talk about this.
No questions? We're good? Okay. So let's talk about solid states or solids. So when we're talking about ionic compounds, we have something like sodium and chloride bonded together, right? This is not the Lewis structure, I'm just, okay? And then, well, if we have one compound of salt, we're going to have trillions of them, right? And so we're going to have something like this. Right? What kind of intermolecular force is that? There's 4 types. What kind is this? Not quite. What kind of compound is sodium chloride?
Oh, it's ion.
Ion because it's an ionic compound, right? And we can continue. And we have something like this. And then right? And that's just one cube. We can draw it forever. We're not going to. But since the intermolecular force is an ion-ion, that's the strongest, right? We talked about this when we talked about ionic compounds, but just to kind of review it a little bit. Salts or ionic compounds are crystalline solids at room temperature. And these are, they have the highest melting point, highest boiling point, all that stuff, right? Because they have the strong intermolecular force out of all the solids. Well, minus just the pure metal, okay? But out of the compounds. Except for one. There's one that's stronger than that. We'll get there. Okay? So for molecular compounds, when I say molecular, I'm talking about covalent compounds, right? Well, we have several different types of solids. Okay, sugar looks like a crystalline solid, but yeah, it is. But the melting point in sugar is a lot lower than in salt, yeah? And that's because it's not an ionic compound. It's got, anybody know what kind of intermolecular force sugar is? It has several. So we'd have to know the structure to know it for sure, right? And I don't even know if this is just what it looks like, kind of like, right? So it looks something like this. Where all of these points right here are carbons, with hydrogens on it, except for some of these carbons have oxygens. Actually, I think, yeah. And we'll just, and it's not really this, guys. It's not. Something like this, right? You have a bunch of carbons, hydrogens, and oxygens in this compound. So because of these guys right here, this is a hydrogen bonding. But because of these guys right here, there's London dispersion, right? And because of this guy right here, there's dipole-dipole. You following? But usually, when we talk about this, we say, okay, what's the strongest? What intermolecular force is going to make this to have the highest melting point or highest boiling point? Okay, so that's why sugar would be considered hydrogen bonding. Good. And so that's pretty high up there, but compared to the melting point of salt, it's way down, right? Okay. And then we have other covalent compounds like butter. Well, it's not that, it's a solid, but it's, well, it melts really easily, right? Okay. So that's because it's what? Maybe more of a London dispersion or dipole-dipole, right? And then, and again, I'm just giving you examples here. I'm not going to have you go out and do this, okay? But the strongest of all of them is a covalent network. Did anybody read about covalent networks? The most common one, well, actually a common one we use every day, most of us use every day, if you have pencils, is graphite. Graphite is just carbon, bonded to carbon, and it has a certain structure, probably something like this. But then it's a network of these carbons, and they're stacked in all directions and stuff. And it makes this a really kind of a really strong, well, so this right here, I don't know if it is a covalent bond, I guess. So they're all covalent bonds, and it's a little bit stronger than to just have an intermolecular force, right? The bond is stronger than the intermolecular force. And so this covalent network, it makes a much, much higher melting point, boiling point. And one that's even better than graphite is a diamond, right? Made out of the same element, just carbon. You ever watch the old Superman, 1980s version? Yeah, it's kind of hilarious to watch, but nowadays special effects are great. But anyway, Superman crushes some coal and turns it into a diamond to give Lois Lane, right? A little bit of science fiction there, but okay. But I guess that's how diamonds are made, right? A lot of pressure, okay? So these things have really, so diamonds really high melting point, boiling point, okay? And then, of course, we have metals. Metals are pretty high as well. And one thing you need to know about metals, so if we have a big chunk of, let's say, copper or silver or gold or whatever, the protons or the nucleus is kind of fixed, and this is not drawn to scale, ladies and gentlemen, okay, and not near as many as there should be, okay. And if you put, let's say, a positively charged particle right here, what happens? All of the electrons, not all of them, but just the valence electrons, the ones on the outside, will end up over here. Yeah? Because metals are like a sea of electrons. So the model is a sea of electrons, meaning they're able to flow wherever they need to go to be attracted to whatever. And this gives metal the property of what? Conductivity, right? Are we good? Okay. In a nutshell, those are solids. Any questions? Okay. Let's take a look at our worksheet. And this is the back side. Let me just give you, so I didn't get a new worksheet. This is just the one from last time. So we have solid type. We have ionic is a type. Molecular. Covalent network. And metallic. Then we have the smallest unit, intermolecular force, and properties, and different examples. So we're just going to kind of fill out this on our worksheet a little bit just together. Sound good? All right. What's the smallest particle of an ionic solid? An ion, a charged atom, right? Cation, anion. Make sense? Smallest particle of a molecular compound or solid is a molecule. So like for water, it's just going to be one H2O, right? Or for carbon dioxide, one CO2. Good? And then a covalent compound are going to be just atoms, covalent network. Like, for example, a diamond, the smallest particle of diamond is carbon, a carbon atom. Good? And then metallic is also an atom, a metal atom, to be specific. Are we good? All right, now let's see if you guys can do the next one, because we just did this last time. What type of intermolecular forces do we have for ionic solids? Ion, ion, perfect. What about for molecular? Dipole, dipole. What else? London dispersion. And hydrogen bonding. Right? Well, what's left? What about for covalent networks? It's just a covalent bond. So like we talked about, like for diamonds, a little bit higher melting point because it's not an intermolecular force that's holding them together, but it's actual bonds, okay? And then,
Do you have another paper? Mine just didn't have a back.
oh, yeah.
Thank you.
And then for metallic, then electron C model. And that's kind of what holds them together. So you have one metal atom, and they just kind of, electrons move in order for them to attract and to hold together. So that's similar to ionic attraction, but maybe a little bit stronger. Okay, and then properties, and we kind of talked about these properties already. Properties of ionic solids: high melting point, boiling point, they're conductive when melted, right, or dissolved. When they're not melted or dissolved, well, they're not conductive, really. So maybe we shouldn't put that one. We'll get there later, okay? Crystalline solids at room temperature. I'll just say crystalline solids. They're brittle. They dissolve in water. Kind of writing that small. High melting point, boiling point, crystalline solids. They're brittle, dissolve in water. Okay. Molecular solids. They're opposite, low melting point / boiling point. And the types of solids, they could be crystalline, like we talked about in sugar. They could be amorphous, like in butter. Yeah. So they're kind of all over the board. And then covalent network, very, very high melting point / boiling point. They're extremely hard. And then metallic is just the properties of metals we talked about before. They're malleable. Ductile. Conductive. Good?
Could you remind me what ductile is again?
Yeah, you can run it into wire.
Oh, okay.
Make wire out of it. So you can, well, it's kind of the same idea as malleable. You can change its shape, and so really run it into wire. But like for the ionic solids, like salts, they're brittle, and so you can't really change their shape. Good? Do we need examples? What's an example of an ionic solid? Sodium chloride. Any ionic compound, right? Magnesium chloride. Which I think that one is that one? What is it? Epsom salt? I think that's that one, okay? And then molecular solids, we have like wax, butter, sugar, petroleum jelly. Kind of the same idea, right? And then covalent networks, we have diamonds, graphite. There's probably others, but I don't know what they are, top of my head. And then metals, we have gold. We have alloy metals like brass and steel. But most of the elements on the periodic tables are metals. Put any of those, right? We good with all the solids? So a lot of that's review. Some of it's new, but any questions so far? So that's just fact stuff, guys. That's not even fun, right? Sorry. Let's get into naming or covalent compounds, naming and writing chemical formulas. And this is the last idea that we'll deal with in this unit. Okay, do you remember the first step in naming or writing chemical formulas for ionic compounds? That's for writing the structure, good. So if as a metal, then we know it's ionic, right? So close to that.
The cation and then
Determine if the compound is ionic or covalent. That's also the first step here. Because I'm going to trick you guys today. Well, let's see if you get tricked. And the reason I'm going to try and trick you is so that you're not tricked on the exam. Okay? So if we get it wrong here, it's not the end of the world, but make sure we learn from it, yeah? Okay. So let's, first of all, name covalent compounds. Step 1, determine the type of compound. That way we know how to name these things. Step 2, name the first element in our covalent compound. As the element name. Does that sound familiar? We're going to add one thing here to make so that it's not the same. Include prefixes, or the correct prefix. And I'll give you those in a minute. Okay, step 3. Name the second element by changing ending to what? IDE. This is the same so far, right? And the difference is include the correct prefix. And I'm going to put a little note on this second step. Don't use prefix if only one atom. And that's just for the first element. We'll use a prefix if there's one on the second element. And we'll do some examples so we make sense of this, okay? And that's it. And we're really only dealing with binary covalent compounds. What does binary mean? Two. Made of two atoms. Two nonmetals. Okay? If you want to do more than that, then you talk to Elizabeth. Take organic chemistry. I'm sorry. I'm sorry. I'll quit bringing that up. Okay. All right, so let's learn the prefixes. Okay, prefix for one is mono, kind of like monotone. Okay, it's just a single tone. Two is di, kind of like dicicle. Wait, I don't know, but we use di. Okay, I'm sure you've heard of di before, right? Okay. Three, we're probably familiar with three. Tri. Four. I kind of helped you to understand four when we talked about molecular geometry. Tetra. Five, like a five-sided polygon, is called penta. Six-sided polygon is called hexa. Seven-sided polygon is called hepta. Not as common, but it is. Eight is octa. Nine, nona, 10, deca. Okay, on your worksheet, the very bottom section 8, section 8, go ahead and try some of those. I'll be right back.
Oh, yeah.
either before or after my yoga on top of it because I'm trying to like.
And then how many?
Don't hurt yourself. And then like. Para hacer práctica.
Yeah, I consider you
And
yoga
I'm
a workout.
Because my husband and I will work out together. Let's do it before your yoga class. And like,
No, you can go to yoga.
I tried to do it. It's really sweet. It's great.
There's only, so for like the first one, would we say that it was, that would be nitrogen or it would be mononitrogen?
Good. What about this right here? We do not use a prefix for the first element if there's only one of them.
But if it has the oxygen after it, then we would.
Yep. Second one, we do.
So would it be nitrogen monoxide?
That's it.
Okay.
Yep. So yeah, NO is nitrogen monoxide. So we use the element name for the first one and the prefix, but since there's only one for that first element, we don't use mono. That's the only prefix we don't use for the first element, okay? So nitrogen, and then there's oxygen. We change the ending to what? IDE, so it's monoxide. We're not going to say monooxide because then it looks like monoxide. Okay? Just try to keep it simple. What about N2O? Anybody? Dinitrogen monoxide. There's two nitrogens, so it's di. Good? What about SF6?
Sulfur hexafluoride?
Sulfur hexafluoride. You guys know what that is? That's the gas that makes you sound like a deep voice. Opposite of helium, right? Never tried that. Tried helium today in my high school kids, and they loved it. Are these pretty simple? Once you get the prefixes down, yeah?
Sorry.
You're good.
N2O4, would you say dinitrogen tetraoxide?
That's right. That's it. Dinitrogen tetroxide.
You
Or,
put like
or
a
tetroxide, right?
tetra.
But it's not a big deal because on the test it's multiple choice, and so I'm not going to say, is it dinitrogen tetraoxide or dinitrogen tetroxide? I'm not going to do that, okay? So it'll be straightforward. We good? Okay. Let's do a couple more. C2H6, K2O, and H2O. H2O is water, but I want you to find the chemical name. So good. Try these ones on your own real quick. If you can do these on your own, you got it. If you can't, well, that's okay. We'll get there. Who wants to give me the name of C2H6? Anybody?
Dicarbon hexahydrogen.
Almost. Dicarbon hexahydrogen. change the ending to
Hydride.
hydride. Yeah, dicarbon hexahydride. Good, good. Who's got K2O? Anybody? Go ahead, Ed.
Dipotassium monoxide.
Is that it? Are we good? Is it dipotassium monoxide? What is it, Elizabeth? Oh, what is it, Manuel?
Is it potassium monoxide? No, there's two of them.
Oh. What is it? It's not dipotassium monoxide. It's not. I told you I was going to trick you, and you guys got tricked. What kind of compound is this? This is an ionic compound. Do we use prefixes for ionic compounds? No. So here's what happens. Every year that I teach chemistry, I get students to make this mistake. Because we learn ionic compounds first and we get good at it, then we change to covalent. And that's the last thing on our head and our brain, so we start naming everything like that. Okay? Do not use prefixes for ionic compounds. How do you know it's ionic? It's got a metal in it. Okay? We was tricked here. Don't worry about it. Just make sure you don't get tricked anymore. I'm not trying to trick you, I promise, on the test. Trying to see if you know this. Yeah?
So you don't put a prefix
You
after?
put it in Roman.
No. Do you put Roman numeral for this one? Why not?
It's not a transition.
It's not a transition metal. We only use the Roman numeral to represent the charge for transition metal ionic compounds. So just let's study that. So this one's just potassium oxide. Done.
Oh,
Because it's a main group element, right? Okay?
So it was potassium what, sorry?
Potassium oxide. Because potassium is always K plus, oxygen is always 2 minus. That means that's the only version of that one. K2O, potassium oxide. Good? And what's water called? Go ahead.
Dihydrogen monoxide.
Dihydrogen monoxide. So yeah, if you have a kid that tries drinking your water and say, oh wait, there's a lot of dihydrogen monoxide in there, watch it. I don't know, kind of dorky, but okay. Okay, let's write chemical formulas. I bet you we can do this without me explaining anything. Let's try it. We have phosphorus triiodide. What are the two elements we're dealing with?
Phosphorus and iodine.
Phosphorus and iodine. How many phosphorus atoms are there? One, because there's no prefix. How many iodines are there? 3, because the prefix is 3. What if there is no prefix on the second one? Then it must be an ionic compound, right? Okay? So if there's prefixes anywhere, this is a covalent compound. What about carbon monoxide? What's the chemical formula? CO, right? It's the gas that's heavier than air, so if we pass out from too much smoke from a fire, we fall down, sinks down to the bottom, and we die. Because we're just breathing carbon monoxide. Call it a poisonous gas, but that's because we're not breathing oxygen, right? It's heavier than air, and it kind of, anyway. Sulfur dioxide, what is it?
SO2.
SO2. Pretty straightforward? Okay. We like these because they're simple. just remember to check what kind of compound are we dealing with. Because the natural tendency is to just name them all like this. And we don't. Okay? C2H2. What's that called? Dicarbon. What? Dihydride. Can we simplify that to be CH, guys? No, never. We only simplify ionic compounds. Only simplify ionic. Good?
Is it a complicated reason why?
No. It's because maybe we have a compound that's CH, and that's a different compound than C2H2, for example. So, why is it that? Why do we simplify it on ionic compounds? So they can be used as least energy as possible, because we just need until it's neutral, right? But for covalent compounds, they're sharing. They can share however many they want to however many atoms they want. Well, shouldn't say they want, but okay, a lot of different possibilities. Good? All right, that is it for exam 2 material. Did we go over the study guide that I sent you? And if you have another question that's not on here, that's fine too. So I emailed this to you. I do have some, if anybody wants one that wasn't able to print it out. But I don't have enough for everybody, so first come, first serve, I guess.
Can I have another one, please?
Oh.
Thank you.
Oh, you get 2, huh?
No, it's one for
You get one? Yeah. Oh, so that means we didn't study this and come with questions, did we? Do you have any questions? Okay, I have a question on 24. So I don't put the problem on here. I just says what you need to know, right? So, yeah. Know why if compounds dissolve. Know why and if compounds dissolve in each other or not. Ooh. It's a good thing we're going over this, isn't it? Huh. I didn't say this because I didn't think it was going to... Uh-oh. Uh-oh. Let's see, make sure I didn't do any other mistakes here. Okay. It's simple. Here it is. Write this down, because you know this is on the test. Okay? Like dissolves like.
Is that supposed to make sense?
It will in a minute. Okay, let's think about something that does not dissolve in something. Oil and water. Is that what you're going to say?
Yeah.
Oil does not dissolve in water in any proportions, right? Because water is polar and oil is nonpolar. Okay? So polar dissolves polar nonpolar dissolves nonpolar. That's it. So I don't think I'll ask you more than that on this test. But on a later test, we're going to deal with solutions and stuff. I might give you a compound that says, which compound will dissolve in this compound the most, right? So you have to determine if it's polar or nonpolar. Say, okay, these ones are polar, so they're going to dissolve, right? But we can do that, right? We know how to tell if it's polar or nonpolar. If we don't, then we need to study that. Do we have any questions on how to tell if it's polar or nonpolar? Okay. What? Yeah. So, for example, water. We said water was polar. How do we know? First of all, we draw the Lewis structure. It looks something like this, right? Then we have to determine the molecular geometry of this. Well, there's how many regions? 4 regions and 2 lone pairs. That means it's bent. Right? So we check the bond. If the bond is polar, then we draw partial positive, partial negative. It is polar, so that's partial negative. Partial positive, that's partial positive. If we can draw a line that separates the positives from the negatives, then it is polar. Good? Yeah.
This is an unrelated question, but will anything that was on the previous exam be on this exam, or is it just this section of what we've been talking about?
Believe it's just this section, but you can look at this. Okay? So, good. We can all thank Manuel for asking this question. Otherwise, I wouldn't have said anything. Okay. Man, maybe you shouldn't have said anything. Then we would all get credit for it. I don't know. Good? Anything else on here or anyone? Yeah.
Number 10.
Number 10. Says, know which compounds dissociate in water. What does dissociate mean? Comes apart, right? Comes apart and then water surrounds it. When does this happen? When something dissolves in it. What dissolves in water? We kind of talked about a little bit today. What dissolves in water? Ionic compounds or salts. So if there's a metal in it, metal and a non-metal, yeah, most likely, not 100% of the time, but most of them, the majority of them, will dissolve in water. In a future unit, we'll talk about which ones don't and which ones do. But for now, salts dissolve in water. Or salts dissociate in water, right? So, did we kind of talk about what happens here? Maybe we should. So, if we have salt in water, it'll come apart, and that's what dissociation means. They break apart, and then we know water is what? Polar or nonpolar? Polar, we just did this. So we're going to have oxygen right here because oxygen is partial negative, right? That partial negative is going to be attracted to that chlorine, or that sodium, the positive sodium. And it's going to do this all around it. And once it's completely surrounded by this water, then we say it is dissolved. What happens on the chlorine? Same thing, but the hydrogens will attract to it because it's partial negative, partial positive, right? And I'm not drawing the exact number, the right number. I'm just, okay, completely surrounding it, right? And if you put more salt in, then there's enough water to completely dissolve it. It won't dissolve them, to just sink at the bottom. Cool? That's what happens when something is dissolved. Yeah, go ahead.
Yeah, there was one problem on the worksheet that I went back to that I had a question about.
Yeah.
It was determining the charge on each atomic or polyatomic ion for the ionic compounds. And it was calcium and then 2 hydrogen. But I was a little confused because,
There's a chemical formula?
so it's Ca
Uh-huh.
and then H2.
Like that?
Mm-hmm.
Okay.
But with calcium and hydrogen, both of them are, sorry. Yeah, both of them have a positive charge.
Mm-hmm. For most of the time. Hydrogen will most of the time be a positive cation. Sometimes it's negative.
So I was wondering what you would label as positive and what you would label as negative, because hydrogen does have a higher.
Okay,
electron-
there's a few different ways to do this. The first element in an ionic compound is which one? The cation, always. The metal is also the cation. Good? So if we want to know the charge of hydrogen, we know the charge of calcium is 2+ because it's in group 2, right? Okay? And there's only one, so that's +2. This has to be -2 to make it neutral because it's an ionic compound. There's 2 of them, so this is a 1- charge. Good? And that's how you do that. Question, Laura?
Number 9, can you explain what you mean by ion and the main group ion?
Mhm.
I'm not sure but what do you mean by main group ion?
Okay, number 9 you said?
Yes.
Know how to classify an ion as main group ion, polyatomic ion, or transition metal ion. Okay? So if we have Ca+, 2+, what kind of ion is that? Main group. It is a cation. It's a main group cation. Well, why? Let's see here. So the main group elements are these ones right here. Good? And so when we name main group ions or cations, we just use the element name, right? Main group anions, we change the ending to IDE. This is for ionic compounds, right? What are these ions going to be? Transition metal ions, right? And then polyatomic ions, well, there's more than one, right? Does that make sense?
Yeah, I was just wondering what the main group was.
Yeah.
Yeah, thank you.
Okay.
I have a hard time like envisioning the mean on number 11.
Okay. Good, and that's why I wanted you to go through these and let's make sure we understand. Okay, number 11 says, know how to determine an unknown ion with a given formula. So, for example, Fe2O3. Know how to find the charge of iron because it's a transition metal. Or if we have FeO, are they the same charge? They're not, they're different. So we have to be able to do that, like what we just did. Does that make sense? Can you do that, or should I do these ones?
And is that all you have to do for that one?
Well, I'm just showing you that's how you do it.
Oh,
Okay, this one it says, with X in place of the ion, and give the number of and with the given number of electrons. Let's do this example. Let's see, I'm using this periodic table so I can, let's do XO2. And the X ion has 78 electrons. What is X? Can you do this? We've never done one of these, have we? Okay, but we should know how to. Do we know the charge of that ion? Oh, do we know how to find the charge of that ion? Yeah, do it the same way we do there, right? So what's the charge of oxygen?
2 minus.
2 minus. And how many oxygens are there? 2 of them. That's a total charge of -4. So the other side has to be +4. And how many are there? Just 1. So it's a 4+ ion. That means X4+ has 78 electrons. Okay. So what does that tell us? How many electrons does X have? Or I guess I should say has. X has how many electrons?
82.
How do you know it's 82?
Because
Because it lost 4 and now has 78. Does that make sense? Because if it's a positive charged ion, it loses electrons. It lost 4, now it has 78. That means before it lost 4, it has 82. So this is an applied problem. If you understand what that positive charge means, we can do this. So if a neutral X has 82 electrons, what element is it? Lead, number 82. Because if it's neutral, the number of electrons and protons are the same, right? Does that make sense? Do you want to do another one by yourself? Let's see, let's do. Okay, the X ion has 10 electrons. Let's figure out what X is. Got it?
I think so.
Yeah. Not quite. Because this is going to be good. Divided by 2. Right? So did everything right except for there's 2 of them. So what's it going to be? 3 plus, right? Does that make sense? Okay. And I want you to also remember this right here is not a metal, so it's going to be a minus charge. So there's something else to help you to realize that you made a mistake, right? Okay, what is it? What is it? 7? What'd you say, Aiden?
Is it magnesium?
Magnesium? Uh-oh. Should we try it? All right. Unless I made a mistake, let's see. Sometimes I do that. I pull stuff out of my head. It's like, oh, what was I thinking? So what's the charge of oxygen? 2 minus. And how many oxygens are there? 3. So it has a total charge of negative 6. Good. This is positive 6. Divided by 2 is 3 plus, right? So the X3 plus has 10 electrons. That means X has how many? 13. It lost 3.
It's aluminum.
Aluminum.
I was looking at the top one with the XO2.
Oh, dang. Yeah, and that happens on the test sometimes. You go write it down on your paper, and you look at the one above it, and you write those down, right? So be careful. Just take your time, double check. Yeah, that's an easy mistake. Questions? No? Would you like another one? Okay. So XS, where the X ion has 36 electrons. Which one? Got it? What is it?
Strong 2.
Strontium, number 38. Good? So we're good with that one? Should I go over it, or we understand? Okay. Anything else? 25? Know how to determine and complete the dipole-dipole interaction. Compare the dipole-dipole interaction of two different molecules. Okay. So, let's say we have HCl and SH, let's see, H2S. Okay? So to determine the intermolecular force, we got to draw the structure, know the geometry, know if it's polar, right? Okay? So HCl looks like this. Sulfur, or dihydrogen sulfide looks like this. Okay, so there's the structure, there's also the molecular geometries, right? Maybe I should do this one's not the greatest example, but it'll help us to understand what this question is asking. Okay, so let's assume they're both polar. They are. The difference here is like 0.4. But remember when I said last time, if you got lone pairs, and you can do the line test, it's polar. End of story. This isn't a real strong polar compound. So what kind of polar compound is this? Hydrogen bonding or dipole-dipole?
Dipole-dipole.
Why isn't it hydrogen bonding? There's hydrogens in there.
The hydrogen bonding is only with nitrogen.
Yeah, it has to be with nitrogen, oxygen, and fluorine, right? So this is dipole-dipole. So make sure we study that, get that down. That's dipole-dipole. And this one right here is also dipole-dipole. Okay? So it says in number 25, determine and compare the dipole-dipole interactions. Which one's stronger? Well, this is 2.1, and this is 3.0. That's a 0.9 dipole interaction, right? This one right here is 2.1 and 2.5. That's a 0.4 dipole interaction. So this one's stronger. Does that make sense?
When would we use this versus like the atomic mass?
Okay, that's when we're determining if what one has a lower or higher melting point.
Okay.
Yeah, so out of these two, which one has a higher melting point?
This stronger one?
Well, let's see. Hydrogen is 1, has a molar mass of 1, right? Plus, chlorine has a molar mass of about 35.5. Sulfur has a molar mass of 32. And we have plus 2 hydrogens. What's that? 34 plus, so yeah, this one's a little bit more, a little bit higher.
Okay, so those two aren't correlated in any way?
They might be a little bit. Because if it has a stronger interaction, it's going to be harder to pull them apart, right?
Yeah.
but I couldn't tell you for sure if that's always the case.
Okay.
We got,
The HCl is a stronger bond.
yeah, because it's got a bigger difference in electronegativity.
Gotcha.
Good? So this one's more polar than this one, right? Well, I'm glad you asked that question. Look at these some more and see if there's others that are kind of, yeah, Laura.
I'm still confused, about how to determine or understanding the electron regions and the lone pairs. I know you gave us but I still, it's hard for me to determine
Okay.
how many lone pairs or electron regions.
Okay, so you have that chart that I gave you, right? So if you know how many, you can read that chart?
Yeah, but I still cause for example, in the first one that was two numbers of electron region, one of the examples were nitrogen, N2, and there's no lone pairs, but then again, the two ends have two little electrons.
Okay,
So
so-
I'm saying
okay, good.
I don't understand it.
All right, so good, great question. Let's do this. So if we draw the Lewis structure, it looks like this, right? Now, to determine the number of regions, we have to pick a central atom. It's just around the central atom. So which one of these nitrogens, and yeah, it's not really central, it's just on the side, okay, but which one do you want to pick? It doesn't matter, they're the same, right? So if we pick this one, how many regions do we have? One here, one there.
That's it?
That's it. So this is linear, yes.
I
It's,
was looking at the whole.
yeah, it's only about the central atom. Good?
In the lone pairs is also an essential atom?
Yes, yep, so this is only one lone pair. Yes,
Okay, yeah, cause I was looking at the whole
okay,
thing and I was just like, wait, there's 6 here,
yeah.
okay.
Yep, so
Central
like,
atom.
like if we have, CCl4, if we draw it, it looks like this. Let me draw it over here. CCl4. And there's all of these electrons around here. So there's not like 59 regions, right? There's only 1, 2, 3, 4 around that central atom. And there's 0 lone pairs. Good?
Yeah, because that was very difficult for me.
Yeah, yep, thanks for asking. Yeah,
Are you going to give us any problems where it branches off into more and you have a central atom like the number? Is there gonna be one of those on a test? If so, can we do one of those?
sometimes I forget if there's that one. I think there is in my 1010 class, but that's not on a test. But we can try it. Definitely wouldn't hurt. So something like, CH3, CH2OH, something like that. So this is ethanol. And you're not gonna have to know that name, that's except for, okay. So if I draw it like this, then that's how it's structured. So we got the carbon with the 3 hydrogens, bonded to the next carbon with 2 hydrogens, bonded to the oxygen with another hydrogen. So something like that, is that what you're talking about? Okay. So, yeah, I won't ask you, okay, what about carbon 1? No, that's more like organic chemistry, okay? But yeah, this one right here is tetrahedral, right? This one right here is tetrahedral. This one right here is bent, right? So which one do you, so if we were to say what kind of intermolecular force this one has, or what the shape is, it depends on which one you're dealing with, right? But the intermolecular force we would just say this is hydrogen bonding. Because that's the strongest bond, the strongest intermolecular force that's here, right? It also has London dispersion. It also has dipole-dipole. But for this exam and for this class, we're just going to say, okay, what's the strongest one? Because that's the one that will determine the different properties. Good? Yeah.
Could you draw the H2O and the molecular geometry?
Yeah.
'Cause yeah.
So do you want me to go in details on how to do it or just draw it?
Yeah, just draw it, because I just want to make sure if I have it.
Okay, so we have oxygen, and we can draw it a few different ways. I like to draw it this way because it's so that it's on the same plane. And then we can draw a lone pair right there and a lone pair right there. And I usually don't draw the wedge and the shaded wedge, but but since there's 4 regions, it is tetrahedral. The electron geometry is tetrahedral, but if we're just looking at the molecular shape, it's bent.
Thank you. I was just trying to remember why you drew the little triangle with the lone pairs, but it's to complete the.
Yeah, it's just to show what the shape is. Because these electrons are really what makes this shape. Not just those electrons, but those electrons as well. And that's why we've got to count how many regions.
Yeah, that makes sense. To
Good.
complete the
To complete the octet.
octet.
hmm
Okay, thank you.
And we do that as far as the Lewis structure, right? Yeah. Good?
Yeah, thank you.
Great questions.
Now I'm confused.
About what?
The difference between the molecular geometry and the electron geometry.
Electron geometry just looks at the electrons. So let me get rid of those. So here we have that is the geometry. Well, I shouldn't have drew it like that. That's the geometry. That's the electron geometry. So it looks like this, right? Which is, let me get these out. This is easier. Electrons make it look like this. So if I take these off, now it's water. But you see the electrons are still the same, right? So that geometry for the electrons is the same, whether it has atoms on it or not. So this is lone pairs. But if we just look at the atoms that are bonded, we kind of ignore these, and it looks bent, right? We can't completely ignore those because these electrons is what makes these electrons do what they do, right? Does that make sense? Yeah, kind of.
Yeah.
Did I answer? I don't know. Yeah, Nancy.
Do 16.
Yeah. 16. Know how to determine if a covalent compound has double or triple bonds. So, how do you know if you should add double or triple bonds?
Draw the Lewis structure.
If, when you draw the Lewis structure, if one of the atom doesn't what?
Have an octet.
Have an octet. If it you use all the valence electrons and some of them still don't have octets, then you keep sharing and you make double and triple bonds. You can't add more valence electrons, so you have to just keep sharing what you have. Make double and triple bonds. Does that make sense?
So you use up all of the little dots
Yeah,
until you don't have any more, but you still have more to go and you put a double bond.
that's right. Then you move some lone pair down to make a double bond or
Yeah.
a triple bond. Okay? Yeah. So really you just need to be able to, okay, draw the structure for that and know that it's not like this, our answers, we're not done, right? We gotta take those away, and make double bonds. Good? Anything else?
To determine, sorry, the central atom, it's the one that has the least electronegative.
The central atom?
Central, what
Yeah.
did I say? Central atom.
Yeah,
Least,
least electronegative element. Also, it's generally the one that's all by itself,
yeah.
but sometimes it's not like that, right?
Why does being the least electronegative make it the same?
Oh, I love that question. I love when people ask why. It's awesome, okay? Because if you understand why, oh man, then if you forget, you can just kind of think about it and make sense of it. Okay, so we have, if we have, let's do, trying to think of one that, carbon, no, that's not a good one. Well, let's just do CO2, I guess. So CO2, so carbon, if we draw it, looks like this, right? And if we, well, let's just, looks like this, right? So carbon has 4 electrons. Oxygen, on the other hand, has 6. If we put one of those oxygens in the center, that oxygen would have less electrons. And, well, we put the one that's least down there so that it can have less and still have an octet. Okay? Does that help?
Is that like if I'm understanding you correctly, you're saying like it, shoot, I lost it.
No, there's another example here. Let's say like HOCl. Which one's the central atom, right? And this one's a little tricky. I'm not going to give you tricky ones. But, so if we had oxygen in the center, then oxygen's more electronegative, right? 1, 2, 3, 4, 5, 6. And chlorine has 1, 2, 3, 4, 5, 6, 7. So chlorine actually has more. It turns out it's okay for this one because they have their original number of valence electrons. You don't need to worry about that. But that's, that's not a great example.
Well, in my mind, I'm thinking it's like it has to, so this, if you have the right central atom, it's sharing the least amount of electrons. Is that
Yeah.
correct?
Yes.
Okay.
It's sharing them but not giving them. I mean, it's taking some from, yeah. Well, I don't know. I mean, the steps that I gave you to do this is probably not how these atoms share. Okay, so for example, if we have carbon dioxide again, we have carbon that has 4, right? Oxygen has 6 each. And so what's going to happen? These guys are going to come over here, share one apiece, and these guys are going to come over here and share one apiece, right? Something like that. But I guess that doesn't tell you why the...
It's hard to explain.
That means I don't understand it all the way, doesn't it? Well, I think I did explain it. You just, yeah, the one in the central atom really doesn't have to have that many. Because if we had, it's hard to find examples in my head.
Is it because, for the central atom, it's like the least complex way for it to come together?
Yeah, uh-huh.
Because if you put a different one that needs more steps, then like, in nature, it's just like, they kinda just want what's convenient.
Yeah,
And, like,
well,
the simplest way to bond will come together, if that makes sense.
yeah. It's because it's simpler that way. And things tend to go the simpler way. Okay, yeah. Yeah,
I got a curious question.
okay.
Why doesn't helium or neon or argon have electronegativity at all?
Good question.
Just a fun question. I'm actually
Okay.
curious.
So here's neon. Does it want any more?
Oh.
It's already full. We say the octet is when electrons want to gain or lose electrons or share electrons to have a noble gas configuration, right?
But like, doesn't krypton also, isn't he also full?
Yeah.
But it has electronegativity of 3.0. It has a strong electronegativity.
Oh, is that what that says? Okay. Yeah.
I'm just
So-
like,
There are always exceptions to rules, and here's what it is. Who makes these rules, guys?
really smart.
People do. People make the rules, and say, okay, this is how it is. Patterns show that this is how it goes. Are people wrong sometimes? Yeah, we find out, you know what? An atom just isn't a ball of mass. It's mostly empty space because we figured out as we get more technology. So maybe when your kids are going to school or when your grandkids are going to school, then we're going to know how it really is, right? Then we won't have these little rules that say now there's always exceptions in chemistry. It's like maybe when your kid's like, there's no exceptions in chemistry, Grandma, right?
We'll see.
Yeah, we'll see. Yeah.
So, question 7, knowing how to tell if a formula is incorrect for ionic compounds. In the mastering chemistry, I had some questions about that because it would give us an incorrect formula
Uh-huh.
and then say, you know, like, how would you change it? But then it wouldn't specify, like, what we were allowed to add or take away.
Mm-hmm.
But correct me if I'm wrong with what you said earlier, with ionic compounds, like, you want them to be simplified to their, the base, right, so it's just neutral, like the
Okay,
base
yeah.
fraction, right? Because when I tried to do that, it was like, actually, no.
Yeah.
Okay. Yeah, let's take a look at it. So we got, let's say we have, can you guys see that okay? SR let's see. So like that. Is that correct or incorrect? Here's how you do it. You draw how it should look if there's strontium and nitrogen. Forget about trying to figure out if that's right or wrong. Draw it. Just write it. And how do we do it? For ionic compounds, we write the charge. Then we cross those charges. SR3N2. Is this correct? No. Right? And if we have a compound, if it says we have iron 2 oxide. Is this iron 2 oxide?
Would be iron.
Yeah, that's iron 3 oxide, so it's wrong for that one, right? So if for main group elements, they have 1 charge. And if they don't have that charge when you go back, they're wrong. Yeah,
That does make sense. Can I give you the
Yes,
example
please.
problem from it?
then I don't have to think of these.
So the one that it gave us was, oh dang it, I didn't actually write it down.
It was the N2H4, right?
N2H,
It was question 8, so I'm not sure if you got the same thing.
I read that.
The one that I had was a combination of nitrogen and hydrogen.
oh, so it's not an ionic compound?
No, I guess it would be covalent.
If it's covalent, then who knows, right? They're not charged. I mean, oh, I guess there's a way to know. So let's see. Should we see if this is a compound? How do we do? Draw the Lewis structure. So we have 5 multiply 2 plus 1 multiply 4. That's a total of what? 14. So far, so good, because it's positive, right? So it's going to be something like this. 2, 4, 6, 8, 10. We have 4 left. 2, 4. They all have octets? Yeah, must be okay. But sometimes they might give you one that it just doesn't work. You just can't make the structure no matter what. It just doesn't work. It must not be real.
I think the one they given was NH3.
Yeah, NH3,
Uh-huh.
that one's real. What about NH4? Is that one real? Let's count it. 5 plus 4, that's 9. Doesn't work. That's why it's not NH4, but NH4 plus. NH4 plus is good because that takes away one of those electrons. Then we have an even number.
I think part of the reason why I was confused is because I did that first step of just simplifying, okay, we just got like the nitrogen and the hydrogen, let's just draw it. And I did get NH3, but then it said that it was actually N2H4 with those elements. So you're saying it could have been either that it was looking for something specific?
What does that question ask? Do you have it?
Yeah, I have it pulled up.
Okay.
So the following formulas are unlikely to be correct, and what it was given was N2H5. And the answer that mastering chemistry was looking for was N2H4.
Mm-hmm.
And I guess that I was confused about.
So what did the question say?
The following formulas are unlikely to be correct. Propose the correct more.
Oh, okay. So it says N2H5? Okay. So we try this, and we get something like this, right? So this is 10 plus 5, that's 15. Well, this is why it's not right,
Right.
because there's an odd number. Okay, but if we have 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 12, 14. Where are we going to put the last one? Oh, it's not going to be by itself. And so we can try N2H6, let's say. Okay, let's put it right there. Well, let's see. Does that work? How many is that? 16, right? 2, 4, 6, 8, 10, 12, 14. But they all have octets. We can't put a double bond. We can't put any lone pairs anywhere because there's no room for them. So, okay, we try N2H 4. Two, 4, 6, 8, 10. 2, 4, 6, 8, 10. And then we have 14, 12, 14. Now they all have octets, and it works.
But we don't reduce because it's not ionic.
Yeah, we never simplify.
That's where I went wrong without remembering that rule, because then I did reduce it and then got the wrong answer the first time. I guess I
Okay.
just wasn't sure the first time around, like, what I could change in
Mhm.
it, what needed to stay. But this makes sense,
Okay.
thank you.
Yeah, draw. So for covalent compounds, you just draw the structure. For ionic compounds, you just find out what it's supposed to be, and then see if it's right. Good. Anything else?
Are you trying to get out of here or something? No, you're good. So, so if it has the prefix, so like we know like monoxide has the prefix.
Yeah.
So it's safe to assume that what we're dealing with here is a covalent. And the first one is like the potassium. Yeah. Yes, so this is because it's an ionic compound. But nitrogen and oxygen are, no, my mom, neither of those are metals, right? So it's a covalent compound. So it comes out to. Now, the reason that like this is because there's only one nitrogen. So we don't say, right? So it's nitrogen, but we do say the second one, one oxygen. She's really nitrogen, one oxygen, right? But never, there's two nitrogen. So we add the suffix for two, so it's dihydrogen, di means two. Right, the di-
Really?
Yeah, right. So it's dihydrogen, one oxygen, one oxygen.
It's nitrous oxide half gas, right?
Yeah. Like, this is a good job. Yeah. So, for the sake of simplicity, if there's the first part of it, there's only one thing. Yeah. But if there's more than one, then we can see how many there are. Yeah. So the second one? No. I better pick on up on it, and that's only.
I wish it's so irritating.
But it's just okay, let's see, like, no, it's ionic.
Who else are you gonna speak to?
Yeah. There would be like,
That's probably kind of good. And you're shocked. I got one in my parents' room for like 5 years. Yeah, I went right through my
I knew that as a grade. The way they did it.
No, pero tú la Ay, pero con esa edad que se ve bonita.
I wish I would have taken it. Because physiology involved.
How are we feeling? If we're done with questions, we're done. But if you have more, I'm here till 9 o'clock, so you're not hurting me to stay later. Yeah.
This, I don't know, this isn't really like a question, but I came across a really interesting example when determining polar versus non-polar molecules for
Uh-huh.
today. Yeah, so it was CH3Cl, which drawing the Lewis structure, for the molecular geometry is tetrahedral,
Yeah?
and the central atom is the carbon,
Mm-hmm.
and it is polar, and it was kind of interesting, at least for me to think that like the chlorine here is so electronegative that it's pulling all of the electrons, and everything, the hydrogen and the carbon, are all positive. Because usually carbon is like, you know, and the hydrogen are pretty equal. But just
Well-
like drawing the line through the like tetrahedral.
Well, this
structure.
right here, this section right here is non-polar,
Yeah.
right? And so all we have to worry about is this bond right there. So, yeah. So if we draw the tetrahedral, it looks something like this. We'll put the chlorine right up there. And we still, whoops, we still draw between the positive and negative. Because this is partial positive, this is partial negative.
Right.
Are we good, or?
Yeah, so it wasn't really a question, it was just an example I had to look at for a while to remember that like that group by
Yeah,
itself
yeah,
was
okay.
like all partial
Yeah.
positive.
Mm-hmm. Yeah. Good. Anything else? Okay, you're not waiting for me. No, you're good. Thanks, take care.
So I tried doing that for the flashcard on Word, and I couldn't paste the images on a blank document.
So,
It wouldn't let me, I don't know why.
on a,
Yeah,
what document? Like a Word?
yeah, like how you told me to do it.
Really?
Yeah, I don't know why.
You have your computer?
Yeah,
Does it have Word?
yeah, I have Word through the school, yeah.
Pull it out.
It's like hard because we write this stuff and then there's like the whole thing. You're like, okay. You look at the paper and you're like, why are we doing the full thing? That's just all like.
Oh, thank you.
Yeah. I'm like, I can go fly with that.
I'll try to.
I sent an email this morning in Canvas for my information for the test to be scheduled.
Oh, yeah, yeah,
I just
yeah.
wanna make sure that you got that.
Yes, let me do that right now. Did you, so you gave me your email and everything?
Yeah, the email and then my student ID just in case.
And did you say when you wanted to take it?
Yes.
Okay, perfect.
Okay, thank you.
I will do that.
Okay, thank you.
I'll do that while I'm waiting for the next class. Yeah, right here.
Yeah, I was just walking out and I was like, I feel like I'm missing something. Thank you. Yeah.
I'm gonna try and get a hold of you, but he's probably not gonna check.
You know, you walk out, sometimes you're like, I know I'm not naked, but I feel like I'm missing
Yeah.
something. It was one of those moments.
Well, good, I'm glad you came back. Because I didn't want to hang on to it for a week.